Hi, my name is Chengpiao Huang. I will talk about model assessment and selection under temporal distribution shifts. This is joint work with Elise Han and Kaizheng Wang. Let me start with the motivation. In practice, we often train statistical models and deploy them into real environments. But the environment is constantly changing over time, and this can affect model performance. As an example, Google developed a fluke prediction model, which worked really well from 2009 to 2012. But in 2013, the model incorrectly predicted twice the true flow level. In this case, it's important to monitor model performance over time and, if necessary, even replace the current model by a better one. We will try to do this using data from a changing environment. In our problem setup, the environment is represented by a data distribution that is changing over time. At each time, we collect a sample from the data distribution. Using this data, we want to do model assessment and model selection. In the model assessment problem, we are given a model, say a linear model or a neural network, and we want to estimate its current performance, which is the expected loss with respect to the current data distribution. In the model selection problem, we are given a collection of models, and we want to find the best one with respect to the current data distribution. Our methodology will apply to a more general setting where we have a batch of samples at each time, and the loss function can take more general forms beyond the square loss. But to keep things simple, we will stick to the square loss and assume one sample at each time. For the model assessment problem, we will take a rolling window approach, and we will estimate the current model performance by averaging data from the last k periods. The question is, how do we choose k? Or what is the right amount of past data to use? This is actually a bias variance trade-off. Specifically, we can decompose the estimation error into a bias term, bk, and a variance term, vk. Using too much past data can lead to a large bias, while using too little data gives a huge variance. The main challenge here is that both the bias and the variance terms depend on the unknown distribution shift and are not computable from data. To get around this, we construct data-driven proxies for both the variance and the bias. And by minimizing this data-driven bias-variance trade-off, we get a window k hat that optimally balances the true bias and variance up to a constant. And so our method adapts to the unknown distribution shift. To tackle the model selection problem, we will use a single elimination tournament, which is based on pairwise comparisons of models. We output the final winner as the selected model. To do this pairwise comparison, we will use our previous adaptive rolling window approach to estimate the performance gap between any pairs of models. Theoretically, we prove that this gives us near optimal model selection. Finally, we conduct numerical experiments to test our method. We consider the task of selecting prediction models on 4 different datasets, each exhibiting a different distribution shift pattern. Our candidate models come from a variety of model classes, including moving average, random forest, and XGBoost. We train each model class on different windows of past data. We will compare our adaptive window algorithm to benchmark algorithms that only use a fixed amount of past data to do model selection. Our results show that For different datasets, due to the different distribution shift patterns, the optimal amount of past data to use is different. But our adaptive algorithm is always comparable to the best fixed window algorithm. So this shows that our algorithm adapts to the unknown distribution shift. Thank you.